Hi everybody. In this video, we're going to take a look at a type of work problem where we calculate the amount of work required to empty and fill tanks. Now for most of our problems here, we're going to have tanks of varying shapes and sizes that are filled with water. Most of the time we're going to use water. Now water has a mass density of 1,000 kilograms per cubic meter, or 1 gram per cubic centimeter. Now usually we're going to use this unit right here, 1,000 kilograms per cubic meter. Now most of our problems are going to be taking place near the surface of the Earth. So when we want to calculate forces required to lift a certain amount of water, we're going to multiply the mass that we want to lift by 9.81 to yield a force. Remember, because force equals mass times acceleration, and near the surface of the Earth, acceleration is about 9.81 meters per second squared. Now, let's take a look at this example to give you an introduction to these problems. So in this example, we have a cylindrical tank that is 2 meters in diameter and 4 meters high. Now, the tank is filled with water, and a pump is located 1/2 of a meter above the rim of the tank. Now we want to do two things here. We want to know how much work is performed by the pump to completely drain the tank of water. And then part B, how much work is performed by the pump to empty half of the tank. All right, now the first thing you want to do with these problems is draw a picture if possible. So that's what we have down here. So here we have a side view of the cylindrical tank. Notice that we have marked here 1 on the x-axis, and this would be -1 over here, right? Because we said the diameter of the tank was 2 meters. The height of the tank is 4, so you see that's 4 right there on the y-axis. And now this is really a cylindrical tank, so you have to realize that, this is a side view of it. So, you have to realize it actually looks, something like this. You have to realize that it really, looks like this. Okay, so this is a side-on view of it. Now, what we're going to do here is the following. We have a pump located up here at position 4.5 on the y-axis. And this pump has a hose that goes all the way down to the bottom of the tank, and it's going to drain this tank of water. So we want to know how much work does the pump have to do to drain this tank of water. So the way we're going to handle this is we're going to think of slicing this tank into little slabs of water, so we're going to have little slabs of water like this going all the way down to the bottom. And what we're going to do is we're going to calculate the amount of work it takes to lift a slab of water up to this height, and then it just goes out the side. And then we're going to sum all of those up, turn it into an integral, and integrate. So that's what we have to do. So here we have a typical slice of water. Right here in the middle, we drew it. So right here is a typical slice of water. Now you have to keep in mind that that is actually circular. So you see right here we have it pictured down here. You see it's a circular slice of water. So we want to calculate how much work it takes to lift this slice up to the level of the pump, because that's what the pump is really doing. It's really picking this slice of water up to this level. That's what it has to do for all of these slices of water. Now, for this slice of water that is located at position Y on the y-axis, we're going to denote the thickness of it by delta Y. Now down here, recall, that's our picture of it. So we have to calculate how much mass does this slice of water contain. Well, we have to calculate the volume and then multiply by the mass density of water, which is 1,000. And that'll give us the amount of force required to lift that slice. Okay, so looking at this slab of water right here, the volume of this slab, this circular disc of water, is going to be pi times x squared, the radius squared, times the height, which is delta y. Okay, so that's what we have right here. Okay. Now, that's the volume. Now, if we multiply that by the mass density of water, which is 1,000 kilograms per cubic meter, keep in mind, by the way, this has units of cubic meters, and this will have units of kilograms per cubic meter. So you see the cubic meters cancel, and you just get units of kilograms. Okay, so that is the mass of this slice of water. Then we need to multiply by 9.8, and that will give us the amount of force it takes to lift this slice upward. Because you see, when I multiply this by 9.8, okay, that's the amount of force that this slice is being accelerated towards the center of the Earth. So to counteract that, we have to push upward with an equal force, and that will counteract it, and then we'll lift the slice upward. Okay, so this is the force that it takes to lift that slice upward, right here. And that's what we have down here. You see we have it labeled F. Now the distance we have to lift it, well, it's going to be this distance right here. You see we lift it from position Y up to position 4.5. So this distance is 4.5 minus Y. Okay, so if we multiply this by 4.5 minus Y, that is how much work it will take to lift this slice of water up to the level of the pump, and then it just spills out, drains out the side. Okay, so we will call that delta W. Okay, so what we have now is dW. If we think of taking really, really thin slices, the delta W turns into a dW. And so that's going to be, oh, and let's note one other thing now. The x here, that's always equal to 1. You see that right there? That's always 1. So we can put a 1 in place of this x right here, okay? So if we put a 1 right there, then all of this can be simplified down to this right here, and we end up with dW equals 9,800 pi times, like that. There we go. Now, what we can do is think of summing all of these slices. Now, summing all of these slices is equivalent to integrating this, so the work is simply going to be the integral of this with respect to y. And you see this y varies from 0, see that's position 0 on the y-axis, all the way up to position 4. Be careful, it doesn't go up to 4.5, there's no water up here. It only goes up to 4. So if we integrate this from 0 to 4, that will give us our answer. Okay, remember the integral is just like summing up all of these little delta w's. And then of course, just integrating this, that's going to be 9,800 pi times, remember that's just a constant. The antiderivative of this is going to be negative 4.5 minus y squared over 2. And then you just plug in 4 and 0 in for the y, subtract those two numbers, and you will get your answer. And we have our answer down here. Let's take a look at it. So you see right here, we have our integral set up. And here is what we just had determined. And you come up with a fairly large number, 307,876.08 joules. That's a lot of work. Well, water is pretty heavy, and that's a pretty big tank. 2-meter diameter by 4 meters high. That's a big tank, and water's pretty heavy, so it's not surprising that it's going to take a lot of energy to empty that tank. Now, if you want to know how much work it takes to empty half of the tank, that's what part B was up here. Remember part B, we wanted to calculate the amount of work required to empty just half of the tank. So we want to drain the water down to, we only want 2 meters of water left in the tank. Okay, well, so what we want to do then is integrate. If we think about this, 9,800 pi times 4.5. Okay, so what are the limits of integration going to be? Well, you see, if we're only going to drain half of the tank, then this y is going to vary from location 2 up to location 4. Okay? So we're only picking up the slices in the top half of the tank. So the y's are going to vary from 2 to 4, so we integrate from 2 to 4, and that's going to be our answer. And let's see what we have down here for that. And so you see, if we integrate from 2 to 4, we get 92,362.82 joules. Okay. Now you notice one thing here. You might erroneously think, well, if I'm draining just half of the tank, shouldn't my answer be half of this value right here, the answer to part A? Well, no, because you see, it takes less work to drain the top half of the tank than the bottom half of the tank, right? Because the top half of the tank has to be lifted a lesser distance than the bottom half of the tank, right? If you look at the diagram up here, you see you have the top half of the tank here and the bottom half. So if you're only draining half of the tank, then you're picking up just the top half of the tank, the water in the tank. And you notice you're lifting each of these slices from like here up to 4.5. But if you're draining the bottom half of the tank, you're lifting the slices from all the way down here up to 4.5. That's a larger distance that you have to lift the slices of water, so it's going to take more work to drain the bottom half of the tank than the top half of the tank. Okay? All right. Now, you can't really drain the bottom half of the tank without draining the top half. You have to go from the top all the way down. But, the point is that the amount of work it takes to empty the tank from here down to here is going to be less than the work it then takes to empty the tank from 2 down to 0. Okay? All right. Now let's take a look at another example. So in this problem, we have a conically shaped tank that is 4 meters in diameter at its top. It is 3 meters high, and the tank is filled with water, and a pump is located 1 meter above the top of the tank. Now we want to calculate how much work is performed by the pump to completely drain the tank of water. So the first thing you want to do with any of these problems is to draw a picture. So down here we have a diagram of the tank. Now right here is the tank. This is a side view of the tank right here. Okay, so that 3, that represents the height of the tank. That point right there is 2 comma 3. This point is -2, 3, so notice that the width of the top of the tank, or its diameter rather, is 4. Now keep in mind, this view is a side-on view. What the tank actually looks like really looks more like this. This is a 3-dimensional rendering of it here. Okay, so that's what the tank, really looks like. This is just a side-on view of it. So now, to calculate the amount of work it takes to drain the tank, what we want to do is think of taking a little slice of water right here. Now this is located at position Y on the Y-axis. And we want to calculate how much work it takes to lift this slice all the way up to position 4 on the Y-axis. That's where the pump is located. And then once we know how much work it'll take to lift this slice, we can then integrate and find how much work in total it will take to drain the entire tank. Okay, so down here we have a 3-dimensional rendering of this little slice right here. Now we want to calculate how much work it takes to lift this slice up to position 4. Keep in mind it is located at position Y right here. So we need to calculate the mass of this slice right here. Okay, well the mass is going to be the volume times its mass density, right? So the volume of this slice of water right here is going to be pi times x squared. That's the radius, right? This distance right here is x. Okay, now that's the area of the base. And then we multiply by the width of this slice. That's delta y, we're going to call it. So times delta y. Now this is the volume of that little slice. To get the mass, we need to multiply by the mass density of water, which is 1,000. Okay, so that is our mass density of water. Okay, so in total here now we have the mass of the slice. Now to calculate how much force it takes to lift this slice upward, we have to multiply by acceleration near the surface of the Earth, which is 9.8. Okay, now what we have here is how much force it takes to lift that slice of water. Now, work equals force times distance, so if we multiply this by the distance we have to lift it, now the distance is going to be that distance right there, which is going to be 4 minus y. So if we multiply that by 4 minus y, then this is the distance, d. This is how much work it's going to take to lift that little slice, and we'll call it our small change in work, or delta W. Okay, now all we have to do is move this delta W. Let's put it at the back here because that's going to indicate what we want to integrate with respect to. And let's also change the delta W and the delta Y into dW and dy's, okay, just to indicate that they're really, really tiny. Okay, there we go. Now what we need to do is think of summing all of these up and taking the limit as the delta y's go to 0. Well, if we do that, remember, if we take the limit of a summation, that is just an integral. So what we need to do here to calculate the total work is just integrate this. Now let's think, we're integrating with respect to y. The y here is going to go from 0 to 3. Okay, so we integrate from 0 to 3. And this is going to give us our total work right here, right? The integral of dw is just a w. Okay. Now there's only one issue that we have here. Let me erase this. And the issue is that this is an x, right? We want to integrate with respect to y. Now we have a y here, that's fine. We can, handle that, integrating that. But we need to put this in terms of y. That needs to be placed in terms of y. Okay, well, if we look back at our drawing here, you see that curve right there. That will allow us to determine a relationship between x, the radius of this disk, and its location y on the y-axis. Well, the equation of this line, you notice we have a rise of 3 and a run of 2. Okay, so very simply, the equation of this line is y equals 3/2 x, or x equals 2/3 y. Okay, so now we can put this in place of the x, and we obtain that this is going to be the amount of work it takes. So if I put 2/3 y in here, what we're going to get is 4/9. I'll put all the constants out in front here. Put all the constants out in front. Pi times, when I square this, I get 4/9. 9800, move that out in front. And then we have the integral of y squared, right? This is going to be a y squared, right? When I square, put this in place of the x, I'm going to have a y squared times 4 minus y dy, and we're integrating from 0 to 3. Okay, now this you can simplify pretty easily, so what we're going to get here is pi times 4/9 times 9800 times this right here. In order to integrate it, you can write it as 4y squared minus y cubed, and then the antiderivative of this, let's see, the antiderivative of y squared is going to be y cubed over 3, so we're going to have times 4/3 y cubed. Okay, right, that's the antiderivative of y squared, y cubed over 3, minus the antiderivative of y cubed is y to the 4th over 4. Let's just write that like this, 1/4 y to the 4th power. And then we need to evaluate that from 0 to 3. So we put 3 in here for y, 0 in here for y, and take the difference. So when we do that, of course, when we put 0 in for y, this whole thing becomes 0. So really our answer is going to be, if we put 3 in here for y, so our answer is going to be pi and so this is our answer. And of course you can clean this up a little bit. This piece right here, if you evaluate that, you'll get 63/4. And so what all this is going to come out to be is pi and of course those 4's will cancel, and you can simplify this or calculate it and get a decimal answer. And the units associated with this would be joules or Newton meters. And so there you go. That's how we handle this problem. Notice the key thing here is to think of taking a little slice of water, calculating how much work it takes to lift that up to the location of the pump, and that gives us the small dW, a small change in work right here. The delta y becomes a dy. That tells us what we want to integrate with respect to. And then we just have to think, when we integrate this, what does the y vary from? It goes from 0 up to 3, and so we just had to integrate from 0 to 3. And also keep in mind that within our integrand, any place that we had an x, we had to write it in terms of y by finding an equation that relates x and y. And that's what the y equals 3/2 x did for us. Now here we have a web work problem that we're going to do. So for this problem, we have that the parabola y equals 3 squared minus x squared, or 9 minus x squared, for x between 0 and 3, is rotated around the y-axis to form a parabolic tank that we have shown down here. Okay, so you take this curve, rotate it around the y-axis, and it forms this solid of revolution, and well, we're just going to think of it as being an empty tank. Now the tank is going to be filled with delicious hot cocoa in celebration of Pi Day. All right, Pi Day, by the way, is on March 14th, 3.14. All right. The tank is filled through an opening at the bottom like this. So we have think of having a tube down here with a pump down here, and it pushes the liquid, the hot cocoa, into this parabolic tank. Now we're going to assume that the mass density of hot cocoa is 1023 kilograms per cubic meter, and near the surface of the Earth, the acceleration due to gravity is 9.81 meters per second squared. We want to find an integral that can be evaluated to determine the amount of work required to fill the tank with hot cocoa. And we want to use the variable y. We want to integrate with respect to the variable y in this problem. All right, so once again, what we're going to do is take our solid and think of slicing it into thin pieces and calculating how much work it takes to move those thin slices. So what we're going to do here, think of, let's think first of all here of let's mark the y and x axes. Okay, so suppose that is your y axis, and your x axis, say, goes like this. Okay, so there's your x and y axes, and this is your curve. In this case, this is going to be the curve y equals 9 minus x squared, right? 3 squared minus x squared. Okay. Now, we want to take a little slice of hot cocoa here and calculate how much work it takes to move that slice from the bottom up to wherever its position is. So now this is a three-dimensional rendering here, but I'm just going to draw it like this. Think of taking a slice like this. Okay, so there we have a slice. Now keep in mind that's actually a three-dimensional disk. This slice is right here. The width is going to be delta y, because it's the delta y is being measured along the y-axis. This is at position y. Okay, and now for this problem, we're actually filling the tank. So when we fill the tank, what we're doing is actually taking this slice and lifting it into place. In the previous problems, we were actually taking the slice and lifting it up to a pump located at the top. Well, for this problem, since we're filling from the bottom, we're going to think of lifting this slice from position y equals 0 up to position y. Okay? All right, so we have to calculate how much work it takes to lift this slice. Okay, so the small amount of work it takes is going to be, all right, we need to calculate the mass of this slice. Now keep in mind that this slice right here, it's actually a disk. Okay, it's a three-dimensional disk. See how the bottom here forms a disk. Okay, so it's actually a disk. So we have to evaluate pi times the radius of this disk squared. Okay, now let's say the radius, this distance right here, that's going to be our radius. We'll call that x, right? That's x right there on the x-axis. Okay, so pi times x squared times delta y. Okay, so that's the volume of this slice right here. We need to multiply that in order to, we want to calculate how much force it takes to lift it, so we want to calculate its mass. So this is the volume times the mass density. Okay, so that's our mass density. All right, this is the volume. And then we multiply that by 9.81. Okay, that's the acceleration, gravitational acceleration. And now this is the amount of force it takes to lift this slice of hot cocoa. All right, now the distance we have to move it is just, we're lifting it from the bottom, so that distance is just y. So we multiply by y. All right. And now all we need to do is integrate this with respect to the dy term right here. So just think of replacing the deltas with d's, dw, dy. Okay, so w, and that should be F right there for force. W is the integral of dw, and that is the integral of all of this. Okay, so we've got pi. I'm going to move all the constants out in front. Okay, and then we have the integral of x squared times y dy. Now, what does the y vary from? Well, the y is going to go from this y, these slices here can go from 0 all the way up to the very top of the tank. Now the top of that tank is going to be at position 9, right? Because if I put 0 in here for x, I get 9 for y. So this is going to go from 0 to 9. All right. Now, of course, the only problem with this is that we have an x in our integrand. We need to figure out what this is in terms of y. Well, this point right here lies on the curve y equals 9 minus x squared, right? That's on the curve y equals 9 minus x squared. So that gives us a relationship between x and y. So this is rather convenient because I have an x squared here and I already have an x squared in this equation, so I don't need to worry about squaring or taking square roots or anything like that. Let's just move this x over here, the y over here. We get x squared equals 9 minus y. And there we go. So our answer is going to be pi times 1023. And there you go. And of course, this is fairly easy to evaluate because what you have in here is just 9y minus y squared. And so those are very easy to anti-differentiate. And so our answer is going to be let's see, antiderivative of 9y is going to be 9/2 y squared minus y cubed over 3. And all of that is evaluated from 0 to 9. So put 9 in here for y, put 0 in here for y, and subtract. Now, once again, if you put the 0 in here for y, you're just going to get 0 back. So really, our answer is just going to be putting the 9 in here for y, and that's going to be our answer. So we get and the units there are going to be joules or Newton meters, and of course you can simplify this if you'd like, or evaluate it on your calculator and get a decimal answer. All right, and so that is how we handle this type of problem. It's not too bad. Just have to think of taking a little slice, have to realize that this is really a disk when we take the slice here, calculate the volume of that slice, multiply by the mass density. This gives us the mass of the slice right here, right? All of this was the mass of that slice. Multiply by 9.81. That gives us the force it takes to lift that slice. Multiply by the distance that we are lifting the slice. Okay? And that gives us the small amount of work. And then we just have to integrate, thinking about what y varies from. And any place you have an x, you have to write it in terms of y because we're integrating with respect to y. So we had to find an equation that related x and y, and that was given from the problem situation here. And that concludes this video about how to calculate the amount of work required to empty and fill tanks of various shapes and sizes.